Today we are going to be taking a look at L'Hôpital's rule. L'Hôpital. This is a French name, and that's how you pronounce it. It looks a lot like La Hospital, but it is pronounced L'Hôpital. Okay, so L'Hôpital is a limits technique. So let's review from our study of limits. How would we evaluate this limit? Okay, if we just plug in -2, we get 0 on top, we get 0 on the bottom. So we look at this and we say, oh, I think I can factor, right? The denominator factors. When we get 0 over 0, my thought is that there's very likely a whole that we can get rid of, that we can eliminate. So can't do anything with the x plus 2, we'll just leave it up on top. X cubed plus 8 factors into x plus 2 times x squared minus 2x plus 4. So now these x plus 2's reduce out, leaving a 1 on top, and x squared minus 2x plus 4 in the denominator, and we can put the -2 into the remaining x's, and we get 1 over 4 plus 4 plus 4, which is 1 over 12. So this limit is 1/12. If I were to graph this function, we would see a whole right at the point -2, 1/12. That's where the whole is. Okay, for this one, x is going to pi. Cosine of pi is -1, so the numerator is going to 0. The denominator sine of pi is also 0. This is 0 over 0. So what would we do with something like this that does not factor? That does not factor, but I can multiply top and bottom by the conjugate of 1 plus cosine x, and we will get, up in the numerator, when we FOIL that out, distribute that out, we'll get 1 minus cosine squared x divided by sine x times 1 minus cosine x. I'm not going to distribute that because I want to get rid of the sine x, and if you distribute it, it's going to be all muddied up there. Okay, 1 minus cosine squared x. We know that sine squared x plus cosine squared x is 1, so 1 minus cosine squared x, if we move this cosine squared x to the other side, we will be left with sine squared x. So this numerator is sine squared x. Now, one of those signs in the sine squared will cancel with this sine x on the bottom, and we will be left with sine x over 1 minus cosine x. Now we can put pi into the remaining x's, and sine of pi is 0, cosine of pi is -1, so that gives us 0 over 2, which is 0. Okay, when we are at a possible whole, we must eliminate it by manipulating the function. Back when we first started limits, we learned to manipulate by factoring and reducing, multiplying to simplify a complex fraction, or multiplying by a conjugate. Now we're adding another option, L'Hôpital's rule. This is a very, very good, very useful technique, but it can only be used if your limit results in one of these indeterminate forms: 0 over 0, infinity over infinity, or negative infinity over infinity. Okay, here's how L'Hôpital's rule works. So, if f and g are both continuous functions, and if the limit as x approaches a of f over g yields one of those 3 indeterminate forms, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. That is L'Hopital's rule. Notice that L'Hopital's rule is not the quotient rule. It does not apply the quotient rule. It treats the numerator and the denominator separately. Let's take a look at some examples. Number 1. If we just plug in 5 for x, we'd get 25 minus 15 minus 10. That is 0. If we just put it on the bottom, we get 25 minus 25. That is 0. So this is one of those that results in the indeterminate form 0 over 0. So to apply L'Hopital's, if it's an FRQ, if it is not multiple choice, you must show, oops, not 0, 5. You must show individually the limit of the numerator is 0 and the limit of the denominator is 0. Now I do realize in this problem I could just factor and reduce and that would be fine. I would just want to show you how L'Hopital's rule works. Okay? So I can take my original limit of f of x, the top, over g of x, the bottom, is equal to the limit as x approaches 5 of the derivative of the top divided by the derivative of the bottom. And now we can plug in 5 again and get 10 minus 3 over 10, that is 7 over 10. That's L'Hopital's rule. Lots of times you will see me put a little LH for L'Hopital where I apply it. Okay? So, again, in an FRQ, not multiple choice, in an FRQ, you must show this step. You must show that the top and the bottom limits are both 0 individually. Okay? Alright, let's take a look at this one. If I just plug in 1 for x, cosine of pi is negative 1, plus 1 is 0. If I put in 1 down here, I'm going to get 3 minus 1 minus 2, that is also 0. So the limit of the top is 0, and the limit of the bottom is 0. This is a good one because how else would we do this problem? If we didn't have L'Hopital's, how would we do this? It would be a mess. It would be a real mess. Okay? So, keep that in mind. So I can write the limit as x approaches 1 of what we started with, is equal to, here's where I am applying L'Hopital's, the limit as x approaches 1 of the derivative of cosine of pi x is negative pi sine of pi x. The derivative of 1 is 0, divided by 6x minus 1. Now we put 1 into the remaining x. Sine of pi is 0. If I put 1 in for this x, I get negative 1. So we get 0 over, I'm sorry, we don't get negative 1. If I put 1 in for this x, we're going to get 5. And 0 over 5 is 0. Okay? So that's how that works. That's how L'Hopital's rule works. Okay, let's do this one. If I just plug in 0 for x, e to the 0 is 1, minus 0, minus 1, so I have 0 on top. ln of 1 is also 0, so each of the individual limits is 0. In an FRQ, we must show that. So, the limit as x approaches 0 of what we started with is equal to, I'm going to apply L'Hopital's, You do not have to write LH there, but it does make it clear. If you're going back and looking at your work, it'll make it clear what you did to get from one step to the other. Okay, the derivative of e to the 2x is 2e to the 2x. The derivative of negative 5x is negative 5. The derivative of negative 1 is 0, divided by the derivative of ln of x plus 1. That's u prime over u, so 1 over x plus 1. Now let's plug in 0 to the remaining x's. E to the 0 is 1. 2 minus 5 is negative 3. If I put a 0 in for that x, I get a 1. So this is negative 3. That's L'Hopital's rule. Okay. As x approaches 0, cosine of 0 is 1. 1 minus 1 is 0 over 0. Both the top and the bottom is 0. So limit as x approaches 0 of just the top is 0, and the limit as x approaches 0 of just the bottom is 0. So the limit as x approaches 0 of 1 minus cosine x over x squared is equal to, applying L'Hopital's, the limit as x approaches 0 of positive sine x divided by 2x. What happens if we put in 0? Sine of 0 is 0. On the bottom I also have 0. I have 0 over 0 again. So I will apply L'Hopital's rule again. The limit as x approaches 0 of just the top is 0, and the limit as x approaches 0 of just the bottom is 0. So the limit as x approaches 0 of the top over the bottom is equal to, applying L'Hopital's again, the limit as x approaches 0 of the derivative of sine x is negative cosine x. I'm sorry, positive cosine x. The limit, the derivative of 2x is 2. Now put in 0 for the remaining x, 1 over 2. That limit is 1/2. Okay? A short historical note, L'Hopital's rule is also known as Bernoulli's rule, named after Johann Bernoulli, who was hired by L'Hopital for some tutoring. And Bernoulli and L'Hopital signed a contract giving L'Hopital the right to use Bernoulli's discoveries however he pleased. And in L'Hopital's first book, most of the work he published was the work of Johann Bernoulli, including this rule. Bernoulli was paid for his work, by the way. That was done frequently back in that time period. Mathematicians would sell the rights to some of their work. But Bernoulli, in his own right, has lots of things that are named after him. And by the way, okay, he did a lot with physics and some of the sciences, as well as math. Okay. This time x is going to infinity. As x goes to infinity. Well, as x goes to infinity, we have a choice. We can do it the way we used to do it, which is we take the highest powered term on top and the highest powered term on the bottom, and we write that limit 5x squared over negative 7x squared. Those x squareds reduce out, leaving negative 5 over 7. I know my answer is going to be negative 5 over 7, but I do want to show you how this would work with L'Hopital's rule. Let me rewrite this limit. Oops, 7x squared. Okay, we do get infinity over infinity, which is a L'Hopital's indeterminate form, so I could apply L'Hopital's rule. The derivative of the top is 10x plus 7. The derivative of the bottom is 4 minus 14x. as x goes to infinity, this is still infinity over infinity. It's still L'Hopital's indeterminate form. So I take the derivative of the top and the derivative of the bottom, 10 over negative 14, which is negative 5 over 7. And that's what we got before. Okay? So I would use this problem, I would do it the way we did it at first. But there are some where we get infinity over infinity that I might use L'Hopital's rule on. Okay? Know that it is an option. Okay, what about this one? X is going to infinity. We have x cubed over e to the x. Okay. What's going on here? It's not like this, right? What's going on? Let's use L'Hopital's rule on this. Let's see what's going on. But we do get infinity over infinity. Therefore, we can use L'Hopital's rule. So I'm going to use L'Hopital's rule. I like multiple choice questions because we don't have to write out all of our work. We know that the top's going to infinity, we know the bottom's going to infinity, we don't have to write it all out. Okay, derivative of the top, derivative of the bottom, still infinity over infinity. So L'Hopital again. 6x, oops, that was a x over here. 6x over e to the x. Still infinity over infinity. So L'Hopital again. 6 over e to the x. Not going to be infinity over infinity anymore because we have a 6 up there. But the bottom is going to infinity. And 6 divided by an extremely large number is going to 0. So this is 0. That means that even though x cubed is a strong function, e to the x is even stronger. And that it makes me think about our strengths of infinity. Where is that stronger function? Where is the stronger infinity lying? Is the stronger infinity lying up on top or on the bottom? In this case it was on the bottom, so the whole thing went to 0. If these were switched, if e to the x was on top, the whole thing would be going to infinity. So, what is the strongest function? Is e to the x the strongest function? No, it's not. We have x to the x is the strongest function. That is so strong that we give him a little nickname called Big Daddy. That is not a conventional nickname. That is a KHS nickname. We've done that for several years now. Okay, Big Daddy. All right. The next up in line, shortly behind x to the x, is x factorial. We call that one Big Mama. When they are around, they are in control. Okay, that's where the strength is. If they are not there, then we look for e to the x, 3 to the x, 5 to the x, etc. 2 to the x, all of those. As long as this base is larger than 1. All of those. Okay? And I don't have a name for that one. I'll let you think up a name if you like. After the exponentials, but those are the exponentials. Exponentials. Okay? After these, there's like x to the first, x squared, x to the fourth, x to the seventh, all of the polynomial terms. Even like x to the 1/2, even that one, okay? So all of those, x to a power, I call those polynomial terms, polyterms, okay? And then after that, bringing up the very bottom, are logs, ln of x, log base 2 of x, all of the logs. Alrighty. Okay, so in number 7, x is going to infinity, and I look, and I do get ln of x is going to infinity, x squared is going to infinity. They're both going to infinity, but they are different magnitudes of infinity. They're different magnitudes. X squared is on another magnitude from ln x. So it is in control. That's where the strength lies. That's where the more powerful infinity lies. So much more powerful that it treats this top one not like infinity, but it treats it like a 1. Okay? So this one is also going to 0. Let's prove that using L'Hopital's rule. I have limit as x goes to infinity of ln x over x squared. Let's prove that this is going to 0. Okay? I do get infinity over infinity, so I'm going to use L'Hopital's rule. So limit as x goes to infinity of the derivative of ln x is 1 over x. The derivative of x squared is 2x. That is the same as 1 over 2x squared. If I multiply top and bottom by x, I get 1 over 2x squared. Now let x go to infinity. As x goes to infinity, we have 1 divided by an extraordinarily large number. That is going to 0. The strength was on the bottom. Okay, what about number 8? Number 8. Okay, well, I see Big Mama. She's hanging around on top. Big Mama on top. This whole thing is going to infinity. Okay, what about number 9? Another limit going to infinity. ln x does go to infinity. Does sin x go to infinity? No. Sin x is at most 1. The largest it gets is 1. The smallest it gets is -1. So we have something that's oscillating between -1 and 1 being divided by an extraordinarily large number, and that is going to 0. A. If I were to, let me grab my calculator, let me show you that graph. If I can grab it here. Let me show you this graph. Let me show you sin x okay, sin x divided by ln x. Let me show you what this graph is. I'm going to do zoom 4. It looks a little funny there, but that's what it looks like. What I do want to do is I want to see what is happening as x goes to infinity. As x goes to infinity, so on my window, right now x is only going to 6.6. So I'm going to change that and make it go to about 20. I'm going to turn off my x-axis ticks so that there's not a bunch of tick marks on there. So there we go. Okay, let's make x go to 100. Do you see it still oscillating? But do you see it also getting closer and closer and closer to the x-axis? Let's make x go to 1000. It is slowly, the little amplitudes are slowly. Let me prove it to you. Let's make y go from -1 to 1. It's really hard to see, but they are getting smaller. Let's go to 2000. Maybe you can see that they're getting smaller. You'll have to trust me that they are getting smaller, because they don't really look like they're getting that much smaller, but they are. It's just that ln of x is so weak, right? ln of 2000 is only 7. So it is going to infinity, but it is going very slowly, right? ln of a very large number is only 16. It's going to infinity just extraordinarily slowly, but it does get there. Okay? So this is true. All right, one more example. Limit as x goes to 0. X is going to 0, so this one's different. Let's plug in 0. Tangent of 0 is 0, minus 0 is 0. Over 0, we got 0 over 0, so I'm going to apply L'Hopital's. The derivative of tangent x is secant squared x. The derivative of negative x is negative 1. The derivative of x cubed is 3x squared. Let's plug in 0 again. Secant of 0 is 1. 1 squared is 1, minus 1 is 0. So again, we get 0 on top, 0 on the bottom. So we're going to use L'Hopital's rule again, right? Now, I'm thinking of, and I am going to rewrite secant squared, I'm going to rewrite that as secant x squared. So all I'm doing is rewriting right now. I'm not applying L'Hopital's yet. Now I'm going to apply L'Hopital's rule. So, L'Hopital's. The derivative of secant x squared. Got to chain rule this. So 2, keep your secant x, multiply by the derivative of secant x, which is secant x tangent x. The derivative of negative 1 is 0, divided by 6x. Let x go to 0. Secant of 0 is 1. Secant of 0 is 1. Tangent of 0, though, is 0. And we have 0 over 0 again. So I need to apply L'Hopital's rule again. So before I apply L'Hopital's rule, I'm going to clean this guy up. This is secant x squared tangent x over 6x, and I just realized I forgot my 2. And you know what I'm going to do just to clean it up a hair? I'm going to change that 6 down there to a 3. Just reduce that. Okay. Now we're applying L'Hopital's rule a third time. Okay, the derivative of the top, I need to use the product rule. I'm starting with my first term, and I'm taking the derivative. I don't know why I put parentheses there. Okay, I'm taking the derivative of secant x squared. So 2 to the front. Keep your secant x, multiply by the derivative of secant x. We reduce the power by 1 here. Multiply by the derivative of secant x, which is secant x tangent x. So that is the derivative of secant x squared. Multiply by tangent x left alone, plus for product rule, the derivative of tangent x is secant squared x. Multiply by this secant squared x left alone, all divided by 3. Okay, let x go to 0. Secant of 0 is 1, secant of 0 is 1, tangent of 0 is 0, tangent of 0 is 0. So this piece here is 0. Secant of 0 is 1, squared is 1. Secant of 0 is 1, squared is 1. So this piece is 1. And we're going to get 1 over 3. C. Alrighty? So that is L'Hopital's rule. A very cool, very useful technique to evaluating limits.